Today we are going to discuss Schrödinger equation for hydrogen atom. So as always, we have an energy operator acting on the wave function. So in other words, kinetic energy operator plus potential energy operator acting on the wave function, giving us the energy of the wave function and the wave function back. The wave function of the electron in the hydrogen atom. We have the nucleus of the hydrogen atom, so one proton, and we have the electron going somewhere around this proton. We don't know exactly where it is, but the solution of Schrödinger equation will give us some information about that. What is the kinetic energy operator? Like always, it's minus h square divided by 2m . And now one small change. Since we have two bodies, we have the mass of the electron here and the mass of the proton, it's better to consider the problem in so-called reduced system of coordinates. So we introduced a reduced mass that is equal of the mass of the electron multiplied by the mass of the proton divided by the mass of the electron plus mass of the proton. Then we can consider the movement of proton and electron separately. But if you look at this one, you see the mass of the proton is around 2000 times larger than mass of the electron. So this one is very small comparing to this. So if we just divide by this, we have here 1 and here we have a very small number. So this is a very close to 1, the denominator. So it's almost mass of the electron, very, very close to the mass of the electron. So it's not a big complication for thinking about the problem. The only difference is that here instead of m, I will be using the reduced mass. Okay, what is the kinetic and potential energy of our system? We know that we have two charges with the minus sign and with the plus sign interacting. The two interacting charges is nothing else like the charge of the first one, proton, charge of the second one, electron, divided by the distance between these two. And the distance between these two is nothing else than x squared plus y squared plus z squared. Very often, probably in your textbook too, you can see also the z here. If there is a z, it means that it is not hydrogen atom anymore, that it is atom with more protons, z protons inside. So they have a charge z plus z electron charge unit. So we can keep the z, it's not really important, but the important part is that it's only one electron there. One electron and one nucleus. So now we have to solve equation, and the wave function, as you see, it's a bit more complicated wave function. We don't know how it looks like, but we know that it's a function of three coordinates, x, y, and z. So three-dimensional differential equation to solve, which is very difficult to solve. And the reason for the difficulty is here. We have a square root of operator in the denominator. This is extremely difficult to solve and very, very complicated equations. And that's why the first thing we are going to do, we are going to change system of coordinates. Usually you get used to that. We always represent position of everything in the space giving the x, y, and z axis. Then if you take a point, you can project it out on this one, having some z coordinates of this one, having some, my plot is not very good. Having the x coordinates of this one and having the y coordinates at this point. But this is not very good system. Why? Because if we say in our equation that x changing from minus a to a, y is changing the same and z is changing the same, then we have that the volume looks like that. It's a cube. So this system of coordinates naturally introduces cube as a unit of volume. But our atom is rather spherical. It's a ball. It's not a cube. So we want a system of coordinates. This system of coordinates is called Cartesian coordinates. From the name of the Cartesius, the guy who invented it. So we have the Cartesian coordinates, and the Cartesian coordinates are not good. They are not symmetric enough for our problem. Our symmetry is a symmetry of a ball. We have a symmetry of a cube in these coordinates. So we are changing the coordinates. We are introducing something what is called spherical coordinates. At first I make a plot and I explain what it means, spherical coordinates. You probably know them already, but it's not a sin to learn once again. We have a point that we can project similarly like we did on the other blackboard. In the z, y, and x. So this point has the coordinates x, y, and z in this Cartesian frame. Now we introduce the new system of coordinates. They will be given in green. First coordinate is the distance from 0. It's called r. Second coordinate will be in blue, is the angle between the z-axis and this r-axis. And this angle is called theta. And the third coordinate, which I put in yellow, is the angle calculated from the x-axis up to this axis, that is the projection. And this is denoted by phi. So now we need a way of changing of coordinates from Cartesian to these coordinates that we can transform our equation in the proper symmetry. Well, it's very easy to find that x, y, and z are given by r, r, r times, times, times. In the case of x, y, it would be sine theta. In the case of z, it will be cosine theta. This is enough for z. For x, you still have to do cosine phi, sine phi. Oh, you can very easily find these equations if you look at this picture and do all the projections. This is not much complications. So this is the transformation from r theta phi inside the x, y, z But looking at the equations here, we rather need the opposite transformation. We need the transformation from x, y, and z inside the r, theta, and phi. This is not difficult either. You can do very fast evaluation saying that r is nothing else than x squared plus y squared plus z squared. You can find that arcus tangens of this angle, it would be equal to z over x squared plus y squared. And you can also find the other one saying that sine of phi is equal, there would be probably y over x squared plus y squared, and the cosine of phi is equal to the x over square root x squared plus y squared. Good. In this case, it's enough to say arcus tangens. The reason is that r is changing from 0 up to infinity. And this is not like that. The angle phi is changing from, angle theta is changing from 0 to the pi. And you know, of course, that pi is nothing else like 180 degrees. And the angle phi is changing from 0 to 2 pi. Now, in fact, here there are different parentheses, like that. Is this symmetry correct? Oh, you can clearly see that if I take something r belonging to A and B, phi belonging to 0 to pi, and theta belonging to 0 to pi, if I take these angles, then you see that this one gives me, in fact, if you plot it outside of this picture, it gives me a ball like that, that has, this one is at B from 0. So this one has nice spherical symmetry. And now we are going to use these coordinates, these spherical coordinates, to change this equation. And what we are getting? We are getting the following thing. This one is going to be changed into minus ze squared. Instead of this ugly root in the denominator, we are just going to have r. So we are just getting the Coulomb law, which we expected. Unfortunately, this one is going to be a bit ugly. So we get better shape of this one, but we get worse shape of this one. This one is going to look like that. Minus h squared over 2 mu. Now I open the parentheses, and to write this down, I have to remove this. So, sorry. If you didn't write anything, you can check in the camera material later. That will be there. So again, the t in the new coordinates will be some, you see that in the old coordinates it was some tx plus ty plus tz. In the new coordinates it's going to be some tr plus t theta plus t phi. So now, how it really looks like? It looks like that. This part is the same, but this equation is becoming, as I said, a bit more complicated. That's the first part, that's the TR. Second part corresponding to theta, I write now, is 1 over r square sine theta. And the third part corresponding to phi is a bit simpler. Good. Not very nice. So there is a question if I should solve with easy operator here and difficult operator here, or it's better to solve with easy operator here and kind of more difficult operator here. Turns out that this one is easier to solve. And the reason is that our new wave function which is the wave function of not x, y, z anymore because we changed coordinates, but it's a function of r, theta, and phi, can be written in the following form as a function of only r multiplied by the function of only theta times the function of only phi. Ah, very nice. So it means that instead of solving one three-dimensional problems, I can solve three one-dimensional problems. It turns out that this is much easier to solve. And this is possible only because in the spherical coordinates it's possible. It's not possible to be done in the Cartesian coordinates, to decompose into x, y, and z, because it doesn't have the proper symmetry. Okay, now you can get the equations, and very often, and I guess your textbook does the same, these two are denoted by the letter y, and it's a function of two angles. It doesn't matter really. But if you really want, you can decompose it further like that. Okay, so this equation now can be decomposed into three separate equations for r, t, and p, or two separate equations into r and y. I'm going to write down the equations. If somebody wants, can do at home all the steps that are necessary to transform into these equations. It's not very difficult. It's a very nice exercise. First, you have the equation for r. And the equation for r looks like that. 1 over r squared d over dr r squared dr over dr plus 2 mu over h bar ze squared over r plus e minus and the other equation for the y looks like that. 1 over sine theta Okay, these are the equations that must be solved in order to find the function r and y. These are a bit simpler than the original problem, but still pretty hard. So what I'm going to do now, I'm not going to solve it, even if it's very beautiful to solve it and show you what are the steps and what are the tricks for solving. We don't have time, unfortunately, for this in this class, but you will learn it in the quantum mechanics class in the future. I'm going only to show you the solutions. So now, these equations have a name. This is called radial equation. And r, as a function of r, is a radial function. Sometimes I will be writing wave function as one word, sometimes as two words. I guess both is correct, but more correct is two words. This one is angular equation. And the y of theta and phi is called spherical harmonic. Now you probably want to know how these functions y look like. They are not very complicated. Turns out that the function y depends on some parameter, lambda. And again, this one also depends on the parameter lambda. This lambda cannot be any value. It must be some special value. Turns out that if this is any value, this equation doesn't have solutions. So this equation has solutions only if this one has a special value. And we are going to discuss in a moment what is the special value. But first, now for different special values of this, you have different functions. So generally I'm going to write this one as functions that depend on two special values, L and M. Let's start. The simplest one is 0, 0. And this one is just given by 1. Function that is everywhere 1. Second one is the function 1, 0. And this one is given by cosine theta. Next one is 1, 1, 1. And this one is given as a cosine theta multiplied by e to the power I phi. Another one is 1 minus 1, and this one is equal as a cosine, I'm sorry, there should be sine here. Times e to the power minus I phi. I'm giving you a few more and we stop here. Next one is 2, 0. And this one is given as, this one is a bit more complicated, cosine square of time minus 1/3. Next one, 2, 1 is given as a sine phi times cosine theta, of course, times e to the I phi. I2 minus 1 is given similar. And the last 2, 2 is equal to sine square times e to the 2I phi, and the last 2 minus 2 is sine square times e to the minus 2I phi. You can ask me how many functions there is. Infinitely many. So I cannot write all of them. The possible values are L equals 0, 1, 2, 3, 4, changing. Possible values for M are minus L plus 1, 0, L minus 1, L. Any questions? Or maybe some error? Here? Here. Sorry. Minus 1 over 3. We said there are infinitely many, and now we are going to explain these things. So the L can be changing from 0, 1, 2. Let's give L equals 0. If L equals 0, M can be changing from minus 0 up to 0. Well, you see that the only possibility is 0. So the only possibility with 0 here is 0 here, and that's this, 0, 0. 1, this one can be changing from minus 1 up to plus 1. So minus 1, 0, 1. 0, 1, minus 1, all functions with 1. These are all functions with 2, with M changing from minus 2 to plus 2. These are called quantum numbers. This is called angular quantum number, and these are called magnetic quantum number. Equation not always has solution. It has only solution if these two numbers have special values. Good. Now there is another problem. This one is real, is 1. This one is a cosine of angle, it's real. No problem. This one, this part is real, but this part is complex. So if we want to plot it, it will be very difficult to plot the complex part of this. It's possible, but difficult. That's why people very often take these two orbitals. You remember that the orbitals 1, 1, 1, minus 1 are kind of brothers. So people very often take these two orbitals and they make a linear combinations. So the combination is, if you take 1, 1, what is linear combination first? Yes. Maybe first definition of a linear combination. If you have a function f and g are functions, then alpha multiplied by f plus beta multiplied by g is a linear combination. Okay? So take the first one, multiply by number. Take the second, multiply by number, and add together. So we know what is the linear combination of functions. Now we can do the linear combination of spherical harmonics. And the linear combination of spherical harmonics is 1 added to 1 minus 1. You can do it together with me. You find that it is nothing else like sine theta e to the I phi plus e to the I minus phi. And we already had this equation before, and we know that this one is nothing else like times the cosine phi. To be more honest with you, I should put here in front of the linear combination the sine 1/2. Then it's exactly the cosine. Now for the other one, I have one linear combination. Now I have the other linear combination by 2I imaginary unit. I have I1 1 minus I1 minus 1. So once with the plus sign, another one with the minus sign. This linear combination, similarly like here, gives me sine theta sine phi. Okay, very nice. So look, this one and this one doesn't have imaginary values anymore. This one is real. So very often, instead of using these two spherical harmonics, you are making a linear combination to get the real value. And very often this one is called y1x, and this one is called y1y. Why, I explain in a moment. You can ask me the following question. Okay, we wrote down 9 of them. Is there any general formula for any ML? Yes, there is. But when you see it, you understand why I didn't want to write it. The general formulas, unfortunately, very often are not simple. In this case, we have something what is called Rodriguez formula. And we have that the spherical harmonics described by ML, usually, sorry, this is written by LM, this order. It doesn't matter, but usually it's that way. LM is given as. Don't expect me to remember this. Not bad. Now this N, L, M is just a constant. As you see, it's equal to 2L plus 1 divided by 2 multiplied by L plus absolute value of M L minus absolute value of m factorial. That's it. Not very nice, but what can we do? Now this P, how is it? L m as a function of cosine theta is given as 1 minus cosine square theta to the power m by 2 d derivative d cosine theta derivative 1 over 2 to the power L factorial, almost finished, L d cosine theta L cosine theta square minus 1 to the power L close. Finished. As you see, this is not a nice formula, but it's general formula. So the good point is you don't have to remember this formula. It's good to know it exists. Now you can complain that the equations I gave you are not exactly the equations given by this formula. Yes, true. I didn't write in the equation on the blackboard these two parts. So these are just numbers, constants. You can find them from this one. Not very important. Important is the functional part, not the normalization part. Now, we have to know, so we can remove angular equations. Still the spherical equations is on the blackboard and it's going to stay there. We have to plot these functions. We have to know how these functions look like. What does it mean, plot function? This is a two-dimensional function. We'll be plotting it in the three-dimensional space. Ooh, sounds terrible. How to plot a function? We have to plot everywhere. So you just set up a number. You say you plot all the points, theta and phi, that the function is equal 0.1. That's simple. So we are plotting all the functions. So we start with function 0, 0. The function 0, 0, if you plot all the points where the function has the value 0.1, turns out looks like perfect sphere. And very often, instead of writing y, 0, 0, people are writing s for spherical. So this is the function s. Then we have the function y 1, 0. Turns out that the function 1, 0, one more important thing. We are plotting the functions where the modulus is equal 0.1. So the sign can be plus or minus. Turns out that this function is everywhere plus. Everywhere positive, never negative. Now we are plotting the function 1, 0. Turns out that the function 1, 0 looks something like this. And again, this is a spherical function. Well, not really spherical in this case, but it looks like that. And the sign here is positive and here is negative. We go further. Next function that I called as a 1y looks like that. And of course it's spherical. No, not spherical, right? It's round. And again, it has here sign plus and here sign minus. The next function that I call 1x looks like that. It has one part here and second part on this axis. Again, spherical, round, cylindric. And again, one of the part is positive, one is negative. So we have three functions. All these three functions are denoted as a function of the type p. This is called pz. This one is called px. And this one is called py. We go further. Not much is left, at least for chemistry. For physics there will be much more left. Next we have the orbitals d. As you see, the L equal 0 gives us the s orbitals. L equal 1 gave us the p orbitals. L equal 2 give us the d orbitals. L equals 3 give us the f orbitals. L equal 4 would be g, and so on. That's how we denote them. So now we want to plot the function d, something what is called z square. That will be the function y20. The function y20 looks like that. If we have the axis z and the axis y and the axis x, the function looks very similar to the function pz. It means it has one part here, it has one part here, again they are round, but except this there is also a part that is here. And this part here looks like a tire of a car. And now, this is positive, this is negative, and this is positive again. We go further. There are the functions d, x, z, and d, y, z. That corresponds to the y, 2x, and the y, 2y. Again, as you probably expect, this one will be the linear combination of 2, 1 plus 2 minus 1, and that would be the linear combination of 2, 1 minus 2 minus 1, and this one is divided by 2i, this one is divided by 2. Now we have to plot them. Let's do it very fast. This is the x-axis, y-axis, z-axis, x-axis, y-axis, z-axis. So if we plot them, we see that there will be the x, z. So we are in the x and z plane, in this plane, and the function has one part here, another part going behind, another part going here, and another one coming here. The plus, plus, minus, minus. This one would be a bit easier to plot, y and z, because y and z is the plane of the blackboard. So we have perfectly nice symmetric function with the, again, plus, minus, plus, minus. That would be the function dx square minus y square and the function dxy. Again, let's plot them fast. So first, x square minus y square will have the poles on the x and y axis, nothing on the z, so it will look something like this. 1, 2, 3, 4. With the, again, plus, minus, plus, minus. And this one will be very similar, but these 4 parts are coming between axes. So one is coming here, other one is coming here, other one is coming here, and one more is coming there. Again with plus, minus, plus, minus. So very simple to imagine. xy, everything is the xy plane. yxz, everything is the xz plane. yz, everything is the yz plane. The z square is a special one. And x square minus y square is also a special one. You see that everything is on the axis. So kind of similar to this one. Here is on everything on the axis z. Here is everything on the axis x and y.